Hello and welcome to an introduction to the normal distribution. Okay, so we're going to start off by thinking about what the normal distribution is and how it compares to the binomial, for example, that we've met in the past. Well, the normal is a continuous distribution, whereas the binomial is a discrete distribution. So, a continuous random variable can take one of infinitely many values. The probability that a continuous random variable takes any one specific value is 0, but you can write the probability that it takes values within a given range. So just going back to our idea of the discrete, consider flipping 10 coins and let x be the number of heads. Then the probability of getting 4 heads is written as the probability of x equals 4, and x is a discrete random variable. Let's say, on the other hand, that y is the average height of a flipped coin, and that the probability that the average height is less than 20 centimeters is written as probability of y is less than 20. Y here is a continuous random variable. And note once again that the probability that y equals 20 is 0, because that's how continuous distributions work. So a continuous random variable has a continuous probability distribution, which can be shown as a curve on a graph, and the area under a continuous probability distribution is equal to 1. The continuous variables generally encountered in real life are more likely to take values grouped around a central value than to take extreme values. The normal distribution is a continuous probability distribution that can be used to model many naturally occurring characteristics that behave in this way. So if you look at the picture, you can see that it's got a sort of symmetrical distribution. The mean, the median, and the mode are all in the same place. So the mode, the highest peak, is right in the middle. The mean, by symmetry, is in the middle, and the median, which is the halfway value, is again in the middle because half the values are to the left and half of them to the right. Okay, and this distribution, as it says, is very common in nature. So examples of continuous variables that can be modeled using the normal distribution are heights of people within a given population, masses of tigers in a jungle, errors in scientific measurements, size variations in manufactured objects, and of course many, many more situations. So as an example, we have some histograms which show the distributions of heights of adult males in a particular city. And you'll notice that as the class width decreases from left to right, the distribution gets smoother. So the distribution becomes what we call bell-shaped and is symmetrical about the mean. And it turns out that you can model the heights of adult males in the city using a normal distribution, and it's defined by two parameters, the mean and standard deviation. And in this case, the mean is 175 centimeters and the standard deviation is 12 centimeters. So characteristics of the normal distribution are, it has parameters mu, the population mean, and sigma squared, the population variance. Of course, that's the same essentially as knowing what the standard deviation is. The normal distribution is symmetrical, so the mean is equal to the median is equal to the mode, as I mentioned earlier. It has a bell-shaped curve with asymptotes at each end, i.e. tending towards zero probability density, and it has a total area under the curve equal to 1. For a normally distributed variable, approximately 68% of the data lies within one standard deviation of the mean, 95% of the data lies within 2 standard deviations of the mean, and nearly all the data, 99.7%, lies within 3 standard deviations of the mean. We're going to have a look at that, what that means in a second. And then over on the right, we've got this normal distribution approximating our heights of adult males. Okay, and as you can see on the graph, it says X, there's a little squiggle, like we use with the binomial distribution, N for normal distribution. 175 is the mean, and then 12 squared is the variance. 12, of course, is the standard deviation, but if we write it as 12 squared, then we've got the variance written there, but we know the standard deviation straight away is 12. So to start off with, I've illustrated this list of, approximately 68%, 95%, 99.7%. I've drawn a diagram to illustrate that. So this is our normal distribution. We have the mean in the middle, okay, as well as the median and the mode. And then as we go left and right, I've added 1 standard deviation, 2 standard deviations, 3 standard deviations, and -1 standard deviation, -2, -3, going to the left of the mean. And so the first fact, that approximately 68% of the data lies within 1 standard deviation of the mean, means that if we go from -1 sigma to +1 sigma, that area is 0.68 or 68% of the total area. Similarly, for 95% lying within 2 standard deviations, I've gone from -2 sigma to +2 sigma. I've written 95% underneath it, but that would be the pink and the yellow regions combined would be 95% of the data. And then to finish this idea off, I've written 99.7% at the top, which covers the area from -3 standard deviations to +3 standard deviations, leaving us with only 0.3% or 0.15% at each end unaccounted for. Another way of looking at the same information is to divide the graph up into 6 different parts. So in the middle, from -1 standard deviation to the mean, that's 34%, because it's half of 68, and then 34% between the mean and +1 standard deviation. If we take our 95%, take away the 68, and then chop that in half, we find that 13.5% of the data is between -2 and -1 standard deviations, or +1 and +2 standard deviations. And again, if we take our 95% away from 99.7%, chop it in half, we get 2.35%. So there's 2.35% of the data between -3 and -2 standard deviations, and 2.35% between +2 and +3 standard deviations. And then if you wanted to look at it cumulatively, so 0.15% of the data is below the mean -3 standard deviations, 2.5%, that's the 2.35 plus the 0.15, is below the mean take away 2 standard deviations. 16% of the data, that's the 0.15, the 2.5 and the 16, is below the mean -1 standard deviation. 50% is below the mean. 84% is below the mean +1 standard deviation. 97.5% is below the mean +2 standard deviations, and 99.85% of the data is below the mean +3 standard deviations. But we can't limit ourselves to only looking at the mean and a whole number of standard deviations away from the mean. Okay, so here we have an example. If I was told that X was normally distributed with a mean of 55 and a standard deviation of 4, but I wanted to find the probability that X was less than 52, I can't use the facts that we've just been looking at, because 52 is 3/4 of a standard deviation away from 55. However, we can use another function on our calculators. So if you use menu 7 and then press number 2, that gives you the normal cumulative distribution. I would normally encourage you to use a lower value of 0. So we type 0 equals. The upper value is the value we've got here, that's 52. The standard deviation is 4 and the mean is 55, and you have to press the equals button twice, one to register the 55 and one to give you an answer. Okay, now the reason the lower is 0 and the upper is 52 is because we're looking at less than 52. In this particular example, we are assuming that there are no values less than 0, of course, but it obviously depends on what the data is, and the probability of that is 0.2266. So that's how you use your calculator, but let's look at 4 examples based on this normal distribution with a mean of 65 and a variance of 16 in 4 slightly different situations. One where m is less than 72, one where m is greater than 66, one where m is between 59 and 74, and one where m is less than 55 or greater than 73. And notice they're all less thans or greater thans. There's no less than or equal to's or greater than or equal to's, because again the probability that any value is specifically equal to something is 0. So let's start off with the probability that m is less than 72. And I am assuming that m has to have positive values. If the standard deviation is large enough, that might be the case, but I'll be explaining that to you later in this video. So for m is less than 72, I'm assuming that the lower can be 0 and the upper can be 72, because we want things that are less than 72. The standard deviation is 4, because it's the square root of the variance, and the variance is 16, and the mean is 65. So don't forget we have to press equals twice in order to get a probability, and the answer is 0.9599. Now we're going to look at the probability that m is greater than 66. So my lower value is 66. For my upper value, there's not really any limit, but I just need to choose a really big number. So I normally go for 9999, unless of course, we're dealing with numbers in the tens of thousands. So the standard deviation is still 4, the mean is still 65. I get an answer of 0.4013. If you want to find the probability that m is between 59 and 74, that's literally what we use for our lower and upper values. So a lower of 59, an upper of 74, still got the same standard deviation and mean, and the probability is 0.9210. I've moved this question so I don't get in the way. We want the probability that m is less than 55 or m is greater than 73. And I suppose, you might think instantly, I'll just do it twice. I'll do it for less than 55 and for greater than 73, which is fine. But an alternative to that would be to actually work out the probability of being between 55 and 73, using the lower as 55 and the upper as 73, which is 0.9710. And then if we subtract that from 1, we'll get whatever's left, which is 0.0290. So I mentioned earlier that sometimes, distributions might take negative values. So I've been using 0 for our lower, and that's usually fine. But if the standard deviation is more than about 1/3 of the mean, then you will need to use a negative lower to ensure you're including all the data. And I can illustrate that in an example. So let's say that we have x, which has a normal distribution with a mean of 27 and a standard deviation of 15, and we want to find the probability that x is less than 32. If I do what I've been doing already and use 0, so my lower is 0, my upper is 32, my standard deviation is 15, my mean is 27, my calculator says the probability that x is less than 32 is 0.5946. And you might just write that down and assume it's correct. However, if I use a lower negative value, like -9999 instead, then I get a probability using the same other data of 0.6306. And that's because the standard deviation is fairly large compared to the mean. Okay, so we've been talking about -3 standard deviations to trap nearly all of the data. But if we take away 3 standard deviations from 27, that's 27 take away 45, which is -18. Okay, so there's lots of data below 0 that wouldn't be included if I used 0 as my lower. And that's why I get a different answer. So the correct answer is 0.6306, but I'm only going to get that if I use a negative lower rather than a 0. So what we've done so far is to work out probabilities based on the mean, the standard deviation, and a value we want to compare with. Okay, now sometimes it works the other way around. We might be given an area or a probability and have to work out what value that corresponds to. Okay, so in this example, we have x, which is normally distributed with a mean of 36 and a variance of 49, hence the standard deviation is 7. And we want to find the value of a such that the probability that x is less than a is 0.7384. So whereas so far we've used menu 7.2, we now can use menu 7.3, the inverse normal. We type in the area, 0.7384 equals, the standard deviation is 7, the mean is 36, and the answer we get is 40.47. Now notice that the calculator is set up to tell you the area lower than when you do this. Okay, so if we wanted x to be greater than a, okay, then we'd have to do something slightly different. We'd have to take away 0.7384 from 1 and use that for our area instead. So we're now going to look at 3 examples with E normally distributed with a mean of 56 and a standard deviation of 5, and I'm going to work out 3 different A values depending on what the probabilities are. So for the first one, we want the value of A when the probability that E is less than A is 0.4721. For our second question, we want the value of A such that the probability that E is greater than A is 0.725. And in our third example, we want the value of A such that the probability that E is between A and 60 is 0.5. So we've got a less than, so we don't have to change the area. So we use menu 7.3. The area is 0.4721. The standard deviation is 5. The mean is 56. And the value of A is 55.65. For the second part, we want the area to be to the right of the value of A. So on that basis, because of the way the calculator is set up, we take away 0.725 from 1. So we're actually looking at an area of 0.275. Again, we use menu 7.3. The area is 0.275. The standard deviation and mean have not changed, and this A value is 53.01. It's slightly more complicated for a between question. So on the left-hand side, the first thing I've done is to use the previous normal distribution function that we've been using before, menu 7.2, with the lower of 0 and upper of 60, standard deviation and mean is still 5 and 56, and that gives me a probability of 0.7881, So that's the probability that E is less than 60. Okay. However, I want the probability that it's between A and 60 to be 0.5. Now, if the chance it's less than 60 is 0.7881, then the chance it's less than A is therefore going to be 0.2881. That's taking away 0.5 from 0.7881. So now I've got an area of 0.2881. I can use menu 7.3 with that area, same standard deviation and mean, and I get a value for A of 53.2. So we're just going to finish off with some conditional probability for the normal distribution. You'll remember the formula for conditional probability. The probability of A given B is equal to the probability of A intersection B divided by the probability of B. So on the numerator of this fraction, we have the intersection, which, as I say, is usually a subset of what is given. So that will happen in our example. So imagine we've got a battery with a lifetime given by T is normally distributed with a mean of 58 and a standard deviation of 6. Given that a battery has already lasted for 60 hours, find the probability that the battery will last for another 5 hours. So we've got some given information that the battery has already lasted for 60 hours, and we want to find out that it's going to last for another 5 hours at least, which will take it to 65 hours of age. So this can be written as the probability that T is greater than 65, given that T is greater than 60. But notice that our numerator will be the probability that T is greater than 65 intersect T is greater than 60, and that is the same as T is greater than 65, since if the battery does make it to 65 hours of age, okay, then obviously it's already made it to 60 hours of age anyway. So that means that we can write the probability of T greater than 65 given that T greater than 60 just as the probability that T is greater than 65 divided by the probability that T is greater than 60. So the numerator is this intersection, but we can just write it as T greater than 65. Then we can use the menu 7.2 function twice to work out the probabilities of T greater than 65 and T greater than 60. And then when we substitute those numbers back into the formula, we get an answer of 0.3293. Thank you for listening.